Hello everyone, welcome back in the course of higher surveying, and we are in module 7, LiDAR grammetry. In the last lecture of this module, we have learned that what is a laser and how laser can be used in order to collect the topographic information. Okay, and then we have seen two forms. One is the wave and another is the pulse. Wave is the continuous emission of the photons, like a continuous turning on of a torch, right? Secondly, the pulse is some collection of photons over a short duration, and that is why when pulse is triggered, we have some number of photons which are compressed or which are sent over a very short duration, and as a result we can compare this phenomena by turning off the torch and turning on the torch continuously. So during the turn on time, we have thrown some number of photons in very short duration, and that is what we call the pulse. Okay, based on the pulse, we have defined a principle called time of flight principle, where pulse will be triggered from transmitter and it will travel through the space, it will interact with the object surface, and it will be reflected by the object. The reflected pulse will be again received at the receiver, and the time between the triggering and the receiving is called the time of flight. By measuring the time of flight, we can measure the distance between the transmitter and the object, or we can measure the distance between transmitter receiver assembly and the object surface. Well, this was the time of flight principle. On the other hand, we have the phase-based principle that we employ with the waves. In case of phase-based principle, what we do, we measure the phase difference of the triggered pulse, we measure the phase difference of the triggered wave and the received wave. So that was the principle. Moreover, in case of pulse, since the energy or the power of photons is triggered in very short duration, and because of that we have very peak energy or peak power of some photons, and because of that we know one thing now, that a pulse can travel for a long distance because it has high peak power. At the same time, wave, which has each and every photon of which has small energy, and that is why although the phase-based measurement is more accurate, but since the photons of the wave cannot travel for a long distance, and as a result we say that we will use the wave for a shorter distances and we will use pulse for a longer distances. That means we will use the pulse for the topographic mapping if the distance is in order of 500 meter, 700 meter, or maybe 1000 meter or more. So that was the idea we have developed in the last lecture. Moreover, then we have seen that if a pulse or a wave is triggered, how to measure the power or the energy of the reflected pulse or reflected wave. By that we see that if the reflected pulse energy or power is less than certain threshold, we will ignore it, or if it is above a certain threshold, we will accept it and will say that yes, we have received the reflected pulse from an object surface. So by measuring the power of the reflected pulse, we will say yes, first of all we have received the reflected pulse, and then we will say that what is the time difference between the triggered and the reflected pulse. So using the time of flight, we will find out the distance that we have learned in the last lecture. So let us learn that how to acquire the data of the topography or the topographic surface using LiDAR. So in this lecture, we are going to discuss about the LiDAR data acquisition using pulse, mainly pulse. Okay, so this lecture is my lecture 2 and it is LiDAR data acquisition. Fine. Okay, the book is still same. Fine. Now this is a typical example of airborne LiDAR data acquisition. Here I would like to specify that we are first going for the airborne LiDAR data acquisition, and we will see why we do it later in this lecture. In this slide, it is shown a typical example of the airborne LiDAR data acquisition. you can see here that there is an aircraft, and aircraft is mounted with the 3 sensors. One is GPS, another is inertial measurement unit, or what we call IMU, and third is the laser scanner, which is sitting at the bottom of the aircraft where I made the dot. Okay. Now you can see here that there is a base station on the ground surface of GPS, okay, and using the principle of differential GPS, I am calculating the position of the aircraft trajectory using GPS rover mounted on the aircraft. Fine. Okay, so we are showing here some GPS satellites to indicate the differential GPS positioning. Secondly, if we look at the IMU, inertial measurement unit, it is measuring some angles, that is the attitude angle of the aircraft motion. So we call it the roll, pitch and yaw. Around certain axes it is measuring, right. Thirdly, we have the laser scanner, and we are showing that it is triggering the laser pulses using time of flight principle, and for each pulse it is measuring the distance between the laser scanner and the ground surface, and so here is the ground surface. So now we can see here that there is some pattern in the jet shape or sawtooth pattern of data acquisition. On the ground surface. So it is like sawtooth, or we also call jet shaped pattern, or we also call zigzag pattern. Right. So there are 3 names, 1, 2 and 3, right. So all 3 names are indicating this pattern of the data acquisition. Okay. So this is the flight altitude of my aircraft, which is shown by the arrow here. Now this is the swath, which is the width of this data acquisition across the flight line. So this is the flight direction here, or what we call direction of flight line. Now this 1.5 meter here, it is showing you the spacing of the 2 data points here and here, right. Okay. Then if I just take one particular line, for example this line from here to here, I can see here that it is acquiring these many number of pulses, 1, 2, 3, 4 and 5. Okay. Each pulse is creating some footprint on the ground surface, right. Okay. So that is creating the horizontal inaccuracy or horizontal uncertainty of the each pulse data of LiDAR. Now, so we are writing here laser footprints, fine, and this is the spacing 1.5 meter, which is existing between the 2 points in a line. So there you can see there are so many lines here, and now in each line we have, let us say, 5 number of points or 5 number of laser pulses are hitting the ground surface, and they are reflected back by the ground surface. And now, so we are recording the coordinates of each and every pulse point, right. So now we can see here that this is the vertical accuracy showing here, these boxes from here to here, some kind of vertical accuracy is there, Z with respect to some datum, right. So let us say Z1, Z2, this is Z3, Z4 and Z5 here, right. So these are the indicating the height elevation of a point with respect to some datum surface, and now this is indicating the uncertainty in the Z value of the topographic point or the point on the ground surface. Well, so this is a kind of typical example of an airborne LiDAR data acquisition. Now, so what is the ideal conditions here? The ideal condition is that we should not change, or there should not be any change of the altitude or the flying height, what we call here the flying altitude, capital H here. So it should not change. That means an aircraft should always fly at a constant height with respect to the ground surface. Further, there should not be any change in the attitude, which means we say that there should not be any change in the attitude, which means aircraft should not vibrate like this. So there will not be any change in the attitude or the roll, pitch and yaw values of the aircraft. The third thing is we should not change the speed. That means aircraft is moving at certain speed, it will always move with a certain speed only. let us say the speed is v, so we should maintain the speed v only. Okay, now there should not be any change in direction of flying, which means if aircraft is flying in certain direction with respect to north, it should always fly in that direction only. And we will see in coming slides why do we expect these kind of ideal conditions, why do we need it, right? Okay, now you can see that there are few elements in this airborne lidar data acquisition. The first is the aircraft and the flying crew. So flying crew is ensuring that there is a smooth operation of the flying operations and the desired quality of the data should be obtained, and that is why they ensure that there should be a smooth operations of the flying, right? Then we have sensors, we have DGPS, we have IMU, and we have a laser scanner. So these are also the participating elements of my airborne lidar data acquisition. Third thing is the user requirements. For example, if you are a user of the lidar data and you have hired some agency to acquire the airborne data, you will definitely ask for certain quality of the data, right? And those qualities are called the user requirements. At the same time, there are some mapping agencies, for example, Survey of India, or we have United States Geological Survey in USA. So such agencies, they also demand some kind of requirements, or they also imposes some kind of conditions, so that the client as well as the data acquisition party both will be having the standard operational procedures, and by following those standard operational procedures, they will be acquiring the data of certain quality. So both parties should fulfill those things, and that is why we call them mapping requirements, right? Okay, so we should understand that what are the roles of these elements, each and every element, so that once we understand these elements, each and every element, then we can ensure that what kind of quality we want and how to ensure that quality of the data, right? So let us go ahead, and first of all, let us look into the first element, that is my instrument or the sensors. The sensors are IMU, GPS, and we have the laser scanner. Now we will talk about the laser scanner, because laser scanner is the first and fundamental instrument that is firing the laser pulses towards the ground surface. So what are the characteristics of the laser scanner? So I am showing in the screen one laser gun, or an overall construction or overall setup of the laser scanner. In the laser scanner, there is a laser gun, and it is continuously firing the laser pulses. Okay, so laser pulses are continuously interacting with the mirror, which is shown here, right? So this mirror is oscillating like this, it is oscillating, and there is a laser gun like that. So right, you can see here, there is a laser gun and it is oscillating. So laser pulses are coming this way, and this mirror, it is diverting the laser pulses towards the ground surface. And as a result, if it oscillates like this, so it will be diverting the laser pulses in multiple directions, not in one direction, right? And because of that, what will happen, I will have some series of points on the ground surface in one line. As we have already shown that there are 5 points, and these 5 points are available because of the motion of the mirror, right? So this is a reflecting mirror, and now we can see in animation how does it work. So there is a ground surface, right, and there is a laser gun there. So let us see, laser gun is firing the pulses, and now I am showing the oscillation of the laser scanner like this. So it is continuously oscillating. Laser gun is also firing the laser pulses continuously. We have so continuous series of laser pulses fired towards the topographic surface, right? So now what is happening here? So these pulses are sent or fired from the laser scanner towards the ground surface, and as a result, we get so many number of pulses on the ground surface, and once the ground surface reflects those pulses towards the scanner, so receiver receives those responses and try to record them. Okay, now you can see here very easily that this length is called the swath. right? Okay, we will talk about all these parameters gradually, one by one. Okay, so what are the characteristics of the laser scanner? Let us try to understand this. Okay, first of all, in the last lecture we have said there are some n number of pulses that can be fired by the laser scanner or by a laser gun in 1 second. So this n number of pulses, those are fired in 1 second, we call it point repetition rate or point repetition frequency. PRF is more popular name for this capital N. Moreover, in this lecture and further in this module, we are going to indicate PRF by F symbol, right? So we can say F is equal to N here, right? Then we have scanning frequency. Okay, as we know that F number of pulses are fired in 1 second by an oscillating mirror and laser gun combination, right? What does it do basically? Okay, so you see that there was a laser gun and it was oscillating like this, perpendicular to the laser gun, right? And now we can see here that it is not possible to fire all the pulses in 1 second. So because number of pulses are very, very high, maybe 1 lakh or maybe 70,000 or 30,000, something in this number. Okay, so what this mirror does? Mirror is basically oscillating, right? And it is diverting the pulses towards the ground surface. Now you can see here very easily that if I fire 1 lakh number of pulses in 1 second, and this will be diverted with the help of scanner. So there is a role of the scanner of this motion, and whatever number of cycles this scanner completes in 1 second, we call it the scanning frequency of the laser scanner, and we indicate it by the small f. Yeah, so I have this is right, and because of the small f, what happens is we have certain number of lines, what we call as the zigzag motion of this one. In general, I can say that the laser scanner always oscillates, or the laser mirror oscillates in one line only. So if my aircraft is stable or hovering at one point like a drone, right, what will happen? It will be creating only one line. However, because of the motion or the speed of the aircraft, it creates zigzag kind of motion like this. And this is the flight line, right? So I am showing now one line here from here to here, and that is called one scan line, right? So now I can see here that it is one complete oscillation of one mirror from this point to this point. Okay, let us say 1, 2, 3, 4, and 5. So I have f is equal to 5 hertz, because 5 times a mirror has oscillated, and as a result we got 5 number of lines of the data. So each line contains some data like this. So now these data points are indicating the topographic information, right? Okay, what is the field of view? So it is the maximum angle, this angle, across which all laser pulses are fired, and that is what we call FOV, and we indicate it by, let's say, 2 alpha. Okay, so with respect to the vertical line, if I have, so we have, this is 1 alpha and this is another alpha. So the 2 alpha is called the FOV of the scanner. Okay, then what is the relationship between FOV and the scanning frequency f? Right, now you can see here, if this is my FOV, and in the FOV a mirror is oscillating like this, fine, in order to divert the pulses. Then what will happen? If this FOV is larger, mirror has to travel more distance, right? And since we have some limited power in the instrument, and as a result we can see that if my FOV is higher or FOV is larger, and so the mirror is traveling for more angular distance, and as a result I will not have higher number of scanning frequency. That means if a mirror has to travel for long distance, it will travel for less number of times. That means scanning frequency will be less, and as a result now I can write that the scanning frequency and the FOV are inversely proportional. So I can write like this, okay, or I can also write now FOV into F is equal to a constant. So generally a laser scanner has this kind of characteristics, and that is an additional characteristics that we should always consider when we go for the airborne LiDAR data acquisition, right. So, let us go ahead with this idea that we have now learned about the laser scanner. So, laser scanner has some more properties. For example, the scanning pattern. We have just talked about the one zigzag pattern or the sawtooth pattern or the Z-shaped pattern. Okay, it can also create some kind of sinusoidal pattern or parallel pattern. We will see these patterns in the coming slides. Now, we have some point repetition frequency of the laser scanner. So, point repetition frequency is generally in the order of 30,000 to 150,000 hertz or so many pulses in 1 second. Okay, flying height. So, flying height is indicated by h. It is in general of order of, let us say, 300 meter to some distance like 3500, although, but this flying height is regulated by the some mapping agencies also, as well as some kind of civil aviation authorities also, right. So, we need to have some special permission in order to fly at certain height, right. Now, we have the swath. We have already indicated what is the swath, and we will go for the mathematical formulation also of the swath in the coming slides. Then each and every laser pulse has some beam divergence, and so it creates some horizontal accuracy or horizontal uncertainty. Then we have point spacing. Okay. In the slide, we have seen that we have two type of point spacing. One is along the flight line and one is across the flight line, right. We will see all the things in the coming slides. Then we have physical limitation that we have indicated right now. That means FOV into the scanning frequency equal to constant. So, that is the physical limitation here. And then we have sequential firing. So, that is another limitation we should always consider. What is the meaning of sequential firing and what is the impact of that? For example, if we fire, let us say, 30,000 number of pulses, what will happen? Each pulse will go and interact with the object surface. It will come back, received at the receiver, and then after that only we will fire the next pulse, right. So, if we increase the height or increase the flying height, each pulse will take more time to travel through the space, and so automatically the number of pulses fired in 1 second or my PRF will be less. So, I can say that PRF is inversely proportional to flying height. Okay. There is one more reason for that, and that we have discussed in last lecture also, that since we need to have more power if I want to measure the larger distance. So, each and every pulse should have more power in order to measure the large distance, so that once it travels through the space and comes back to the receiver, it will have enough energy that is reflected from the object surface. And as a result, we say if I have a limited power, then I can fire limited number of pulses. So, if I need to provide each and every pulse with higher energy, so it can travel in for a larger distance or larger flying height, what will happen? Automatically the number of pulses will be less if I increase the flying height. So, you should understand these two fundamental reasons. So, what is the impact of the sequential firing here? Okay. So, now we have understood what are the characteristics of the laser scanner. So, now let us understand the scanning patterns that is created by the combination of the aircraft speed and the laser scanner movement. So, the laser scanner is diverting the pulses or throwing the pulses across the direction of flight. So, these three lines are indicating the flight directions, fine, all these three. And now we are going to show you three patterns of the laser scanning, right. This is the first pattern where laser pulses are fired, and because of the aircraft speed, they are being collected in the Z-shaped or what we call sawtooth pattern. So, this is the sawtooth pattern or the Z-shaped pattern, right. So, these are so many pulses fired in 1 second. Now, we can see here that what is my scanning frequency? I can see here that is, let us say, 0.1, then 0.2, 0.3, 0.4, right. So, we have 1, 2, 3. So and it is showing 3.5. In fact, it does not happen. Generally, we have complete 4 here. So let us draw few more points here, and it is my scanning frequency is f equal to 4 hertz here, right? Okay. Now let us look into the next pattern, that is parallel pattern. So parallel pattern is like that, where we create parallel lines. So now you can imagine that in case of Z-shaped pattern, if we remove these lines, alternate lines, this line, and then this line and this line, I can create these parallel patterns. That means oscillating mirror is acquiring the data in only one turn, not in the return turn, and we can have the parallel pattern. Apart from that, we have one more pattern which is called sinusoidal pattern, where data is acquired in this fashion. As aircraft is moving and laser scanner is mounted over the aircraft, and so because of the movement of aircraft and laser scanning firing, we can create this kind of pattern, and that is called the sinusoidal pattern here, right? See, this is the sinusoidal pattern we have created here. So these 3 kinds of patterns are possible to create. Also, there are some other patterns also are possible. However, if you see that Z-shaped pattern is most dense data collecting pattern, and so it is most popular among the all scanning patterns. And so we are going to use this Z-shaped pattern only in this lecture. And again, I can say that it is very easy to understand. So once you understand the Z-shaped pattern or sawtooth pattern or zigzag pattern, then you can derive other patterns also. So now let us understand the role of the DGPS and IMU. So DGPS is differential global positioning system, and now you can imagine that aircraft has DGPS mounted over the top of that. So now it is in connection with the all satellites, and satellite lock is maintained, right? So what happens here? It is acquiring the data at every 1 second. So at every 1 second, it is acquiring x, y, and z position of the aircraft trajectory, right? During that 1 second, as we have said that we are firing f number of pulses. So what will happen during that 1 second? During that 1 second in which we fire f number of pulses, IMU acquires roll, pitch, and yaw of the aircraft trajectory or the aircraft motion. Because of that, we come to know what is the motion of the scanner, or how scanner is behaving like that with the aircraft. As a result, we can see that if we interpolate the values using the roll, pitch, and yaw, so then we can find out the trajectory of the aircraft between that 1 second also. And now we can see that for each and every pulse, we know what is the value of aircraft trajectory. And using that information, we can find out what is the coordinate for each and every pulse. And that is the role of IMU here, okay? So these are the characteristics of the DGPS. It basically observes the 3D coordinates of aircraft trajectory, and it updates the data at every 1 second, or what we call 1 hertz. So the lock should be maintained. That means if my aircraft is moving like that and it turns after some time back to the next line, what happens is my lock should be maintained. Otherwise, if lock is lost, I will not get the GPS data. And that is the first condition we should consider when we integrate so many sensors and all the elements like aircraft and other things. Okay, so banking angle is restricted, as I already told you. Okay, let us see the characteristics of the IMU. It observes the roll, pitch, and yaw, fine, and then it measures the roll, pitch, and yaw with respect to true east, true north, and the gravity direction. Okay, so data rate is 60 hertz to 250 hertz. It depends like which quality of the IMU you are using. Okay, now there is another problem with the IMU. It sleeps on the long flight lines. What's the meaning here? So if we are carrying the IMU in an aircraft is continuously traveling in one line in one direction for more than 15 minutes, now what will happen? IMU will start accumulating the errors, and that is the problem with the IMU. And as a result, we should regularly turn the aircraft so that IMU should not sleep. Okay, now if we see that if my aircraft is moving at a speed of 50 meters per second, which is a common speed, generally we have the speed in the range of 50 to 70 meters per second. Let us say it is moving at a speed of 50 meters per second, and for 15 minutes, how many seconds we have? So many seconds. And so what is the distance here? 15,000 meters, which is 15 kilometers. So in general, we can say that flight line or one flight line, it is not so long of 15 kilometers. And as a result, we have to take a turn. And so this condition does not create much of the problem in the data acquisition. So nowadays, we are very much relaxed as far as IMU is concerned for the airborne data acquisition, right? Okay, so now we have understood what is the role of the DGPS and IMU. Okay, now let us say that we have used IMU, we have used DGPS, and we have find out the trajectory of my aircraft. So this is the ideal trajectory, and this is the flight line on the ground surface. Fine. What will happen now? Because we know the trajectory points on each and every point within 1 second also. Okay. So now we can say that laser scanner, when mounted on an aircraft, it is acquiring the data at each and every, even the fraction of second. So let us look this thing by animation. What does it mean? So this is my flying height. So now my radar data is acquired by movement of the aircraft and operation of the laser scanner. So it is zigzag pattern or the jet-shaped pattern. We are acquiring the data, right? So this is my aircraft trajectory here, and we know the coordinate of this trajectory from even the point to point or even over a fraction of second, we know. And as a result, now we can find out what is the coordinate of each and every pulse on the ground surface, right? So that is the mechanism one should understand for the airborne LiDAR data acquisition. Okay, so we got this kind of data over the time. As aircraft moves from this point to this point, we got this kind of data, or what we call is in the zigzag pattern of the data. Now, this is two lines are indicating the swath here. Right? Okay. Once again, try to learn what is the swath. And so let us say there is a flight line and this is my flying height. Fine. So we have acquired this data. Right. Now aircraft will turn on the next line. So this is my swath here. Right. So now aircraft will turn on the next line. So this is the next line here, and so this is the flight line, and this is my flight line on the ground surface, this one. Okay, let us acquire the data like this. Aircraft scanner is again acquiring the data. Now we can see one more swath. So this is the swath again, right? And we can see there is an overlap here. This is my overlap here between the two swath, and that is called the overlap. Okay, so now you can understand what do we mean by overlap and what is the swath. Okay, so we are plotting the flight lines on the ground surface or on the map. So we are getting these two flight paths. So the difference between the two flight paths, it's called effective swath, or the spacing between the flight lines is also called the effective swath, right? So now we can see here, we will go for the derivation later. Okay, now we can see here, we are indicating the flight lines here, and you can see here the flight lines, and then flight path. Flight path is indicated on the map. So this is my map here, which is showing by XY, and so we have an area of interest, which is written here as AOI and indicated by the black line. You can see there is a closed polygon indicating the AOI. Now we have divided these AOI into the parallel lines, and each parallel line is called flight strip, right? So I write it, each strip is called flight strip, and the center line of the flight strip is called the flight path, and which is nothing but the vertical projection of the flight line, right? So let us say, in order to acquire the data, aircraft is starting from point S, that is my starting point, and it will travel over this line from this point to this point. Then it makes a turn like this, and again from this point to this point it travels in a straight line over the flight strip, and it acquires the data in a zigzag fashion like this. And then it will exit from this point here. Again it will go and come back to this next line, and again it will acquire the data like this in a zigzag pattern. So each line is indicating some data, and it will then exit from this point, and it will repeat the whole process, and finally from point E aircraft will exit and go to the airstrip. Okay, so now we can see that each and every line has some data like this, right? I hope that you have understood the mechanism of the airborne laser flying operation as well as airborne lidar data acquisition. So before we go into any derivation, we should know this thing. Okay, what about the spacing between the flight lines? This is spacing. It is nothing but the effective swath that we have shown in the last slide, right? Okay. So now let us go for the small derivations. Okay, what is a swath? Now, if I take, this is my FOV as 2 alpha, and this is the flying height, and this is the ground surface, which I assume as flat and horizontal for simplicity. So this is the flying height h, and as a result I see that this is my swath. So now the flight path is perpendicular to this plane, and so swath is given by 2h tangent of alpha, right? Okay, what is the overlap? If I have two swaths, you can refer back the slides again in order to better conceptualization. So let us say this is my one swath here. So this is my flying height again, h here. Okay, now let us say we have some effective swath, and again we are repeating the process. So this is my flying height again, and so aircraft is moving from this point and coming back onto this point. So this is my effective swath, or the spacing between the flight lines. Okay, this is my overlap from here to here, and this is another swath here to here. So between the two swath we have overlap, and overlap is given by some percentage of the swath. So let us say if eta percentage of my swath. So I can write here eta times 2h tangent of alpha, and that is my overlap. Okay, what is the spacing between the lines or effective swath? You can see here that this is my overlap, right? And now this distance from here to here, this distance from here to here, it is constant. That means here it is like this, here it is like this, and here it is like this. And so this is called the effective swath, or the spacing between the flight lines, and it is given by, you can see here that effective swath is nothing but swath minus overlap. So I can write here 2h tangent of alpha minus eta times 2h tangent of alpha, or I can also write 2h tangent of alpha into 1 minus eta. Eta, which is my overlap percentage, is generally expressed in the percentage, for example 10%. So it becomes 0.1. So if I put here 0.1, I will get 0.9 times of my swath as my effective swath. So this is the simple concept of the swath, effective swath, and the spacing between the flight lines. So now you can easily correlate each and everything. Okay, so we have learned how scanners are there, like DGPS, GPS, and laser scanner, right? So what are their characteristics? Then how do they create swath? How do they create each and every laser pulse? and each and every laser pulse is creating some kind of footprint, and it is also creating some kind of vertical accuracy. So we have seen all these things in this lecture, in the previous slide, or in the last lecture. Let us look into the user requirements. So what is the user requirement? User requirement consists of two aspects. One is the project requirements, and the second is the mapping requirements. And then we derive some terms called resolution of the data that we'll see later. But before that, try to understand what is the project requirement. So each and every project has some requirement about the data quality as well as data quantity, and these are called the project requirements. And these are data density, data spacing, overlap, and the errors. We will see one by one all this. But before that, let us look into the mapping requirements. So what is the mapping requirements? Each and every mapping agency demands some kind of attributes or some kind of quality or some kind of conditions in the data acquisition process, so that data should have some minimum quality. And so we say that my data should be uniformly spaced, which means if the data is uniformly spaced, I can create a uniform product, or the 3D data or the 3D digital elevation model will be uniform, and we will have more confidence into that. Now, there should be minimum overlap. We can see here, if I increase the overlap, first of all, I will not get any additional information, because we are getting some information in one side or one swath. Again, there is no point of repeating that information again, right? As a result, we will have minimum overlap. Moreover, there is one more reason for that. Minimum overlap will increase the distance between the flight lines, and I will acquire the data of a given area in minimum time. Why? Because I will have less number of flight lines. You can see this thing there. That means if the effective swath is more, I will have less number of flight lines, and less number of flight lines means less number of turns, and so overall time of data acquisition in air will be minimum. And that's the reason we prefer the minimum overlap of the data. At the same time, we should understand that overlap cannot be made zero, because overlap is must, or it is required in order to maintain the continuity of the data between the two swaths or between the two flight strips which are adjacently located, right? And that's the reason we do not minimize or do not make the overlap equal to zero. We have minimum overlap always, right? So let us go into each and every term one by one. First of all, we'll go for the data density. Let us see, this is the flight line, and now we have acquired this data in 1 second. What does it mean basically? This is the swath you can see here across the flight line, and this is the speed of the aircraft. That means aircraft is traveling by so many meters in 1 second, and that is what we call the speed of the aircraft, right? So I can find out what is the area of this data. I can see here the rectangle of the area of the rectangle here is Bs into V. Now this area is containing so much of point data, what we call LiDAR data. Now I want to find out what is the quantity of the data per unit square area, and as a result I can say that since I am firing f number of pulses, so I define a data density or number of points over unit meter square or unit area as f, that is number of pulses fired in 1 second, and during that 1 second area covered by the area covered, right? So this is the data density. Generally, if I take the unit of data density, it will be points or divided by meter square, because this is the unit of area meter square and f has number of points. So I have unit called points per meter square, right? So this is my data density. Okay, let us look further. So if I zoom in this area, we can see that there are two lines of the data here, and it has some data spacing. What does it mean? These 2 points which are falling in one scan line, or we can say two scan line, in one oscillation or one cycle. So, this is the data spacing between these 2 points. Moreover, I can say this is the shorter data spacing between this point and this point, or this is my. So, let us call as a long spacing, this one my along track spacing, long spacing, or this is one spacing is the along track spacing in the short spacing. Why? Because this is the flying direction here, right. Now, we can see that this is the along the flight line. So, I am saying along flight line spacing or along spacing, and you can see here that along spacing is given by dA. Let us say I am writing it L first. This one is given by this V by F, where we have the scanning frequency F. Why? Because you can see here we have one cycle here, then we have second cycle starts here, third cycle, fourth cycle, and fifth cycle. So, I have F is equal to 5 hertz here. Now, if I divide here, I will get this distance, or I will get this distance as my d along spacing, the longer spacing. Now, what about the shorter spacing? The shorter spacing will be given by V divided by 2 times of F. Is very simple, you can understand it now. So, it is up to you which spacing you specify if you want to acquire the LiDAR data by airborne method. Okay, let us go ahead. So, these are my project requirements. One is data density and one is the data spacing, because data spacing is going to tell me how much data is apart from each other. Okay, one more thing I would like to introduce here, the spacing between the 2 points here, or the average spacing between any 2 points here along the swath, and that is spacing is called the across track spacing. Right? Fine. And I am writing it with the help of ds symbol. So, ds is given by, I can say that is my swath here, swath divided by number of points in one line. Or one scan line, right. So, what about the number of points in one scan line? These many points are there, right. How can I estimate it? It is very simple. Okay, let us say we have f number of points in 1 second, and now we have scanning frequency as 2f, sorry f. So, if we divide f by 2f, I will come to know about these many points in one line, right, because there are 2f number of lines and these lines are containing total f number of data. So, now the number of data is this much. So, what is my ds is given by bs upon f by 2f, or I can write it 2f bs upon capital F. This is my ds, or the spacing or the average spacing in the across track direction. At the same time, data density is going to tell us that how much data is available in unit square area. Now, we see the LiDAR data errors. There is one more requirement, that is errors. We can see here that there are 4 elements are there. For example, 3 scanners, GPS, IMU, scanner, and then they are mounted in the aircraft. So, aircraft trajectory also has some error, and as a result what happens is a user specify that I want the data quality up to so and so limit, and similarly he has some criteria for the vertical direction error. Now, all these 4 elements are contributing to the error of the data, and as a result we have some planimetric error and we have altimetric or vertical error. So, let us see, this is my error ellipsoid and this is the planimetric error, ellipse of the planimetric error here, and then we have 2 sigma p here, right. Sigma p is nothing but the planimetric error. Now, we have altimetric error also here. So, this is my altimetric error sigma v here. So, we are writing that okay, we can tolerate, a user can tolerate this much of error given by sigma p in horizontal and sigma v in vertical. So we should also try to meet these requirements once we acquire the data in the field. So now if we see the overlap and the spacing between the flight lines, again we are looking at very carefully. This is as the overlap, and we have already given the formula of overlap is eta n times 2h tangent of phi. So the spacing between the flight line is given as swath minus overlap. I am repeating it, and so we have 2h tangent alpha 1 minus eta, right. So this is spacing is this much. Okay, as we know that spacing is higher, it is beneficial to us because it will reduce the overall cost of the acquired data. So it is required. At the same time, we cannot make the overlap equal to 0 because overlap is also required in order to maintain the continuity of the data between the data of two flight strips. Finally, I am now summarizing the all project requirements. So first is the error, then we have data density, then we have data spacing, then we have overlap. Okay, so let me write the minimum quantities. So minimum quantity of the overlap is, we have 10%, fine. Data spacing, it should be uniform. That means the along track spacing and the across track spacing should be uniform. Okay. What about the errors? Errors should be generally given by sigma v, let us say some 15 centimeter, and similarly it is given sigma p equal to something. So these errors which are obtained in the LiDAR data should be less than by the maximum error, like this. Okay, what about the data density? Data density is, for example, a user says I want 5 points per meter square. So this kind of requirements we should be able to satisfy by the airborne data operation using scanner, GPS and IMU, right. So generally a user demands that the spacing in the two directions, that is my DS and DA, it can be long spacing or short spacing, they should follow some uniform direction. That means we say that DA minus DS, they should be within some threshold, let us say delta, right. Or I can also write that DA minus DS mode divided by DA should be less than equal to some threshold delta T, which is in percentage. Okay. So these are the important things we should understand as a project requirements. Let us go ahead. Okay, what about the resolution of the data? So far we have talked about the data density, and we are saying that the data density is number of data points over a unit square area. However, if we see carefully, the data density is determined by a large area, that is swath into speed. So that is the kind of an average criteria over a very large area called swath into velocity or the speed of the aircraft, right. Now I want to estimate my resolution or the quality at each point in the data set. What can I do? I can find out the resolution now, and resolution is nothing but the distance between the 2 points or 2 data points. Now if you see here carefully, if I draw the mechanism again here, so we are firing some points in one line, let us say these many points we are firing. So we can see here that my alpha value, that is the alpha here, this alpha value is 0 here, and as a result we get some kind of footprint here, right. And so what will happen, the spacing between the points from here to here will be less, like this, for the 2 consecutive or sequentially fired pulses. But if we see here, the data distance between the 2 data sets, 2 data points from here, it will be very, very large. And so we define 2 terms. One is the worst case resolution and one is the best resolution. The best resolution we get at the nadir, this, and that is given by Rn h into tangent of delta alpha. And delta alpha, if you remember, that if I divide 2 alpha into number of points in one line, I will get my delta alpha. So this is nothing but the delta alpha is the angle between two sequentially fired pulses by the scanner. So that is the resolution here I get. Okay. Now we can see what is my horizontal resolution in the worst case, which is here, RH here. So this is my Rn here and this is my RH here. So this is my RH or R horizontal, right, and it is given by Rn into sec square alpha, where this complete angle is my 2 alpha or the half angle is my alpha. So this is my half angle here or half of the FOV. So I can write here alpha is nothing but FOV by 2, right. Now what about the vertical resolution? So we have determined that there is a horizontal resolution here for the given delta alpha. This is my delta alpha, and so we have higher spacing here. So it is my worst case resolution, or what we call is R horizontal, right. Now if we for same delta alpha, I have points very high resolution over there. So this is my Rn at nadir. Now what about the vertical? Let us say there is a building like this and then these data points are fired like this. So you can see here that the vertical resolution is worst at the bottom of a building, right. So now this vertical resolution R vertical or RVER is given by Rn times tangent of 90 degree minus alpha minus delta alpha, right. So it is again the worst or the minimum resolution. So we should understand this also. Fine. Now coming to the flying operations. So far we have discussed about all the data quality, project requirement, mapping requirement, scanner quality, GPS, IMU and so on. Now we will talk about the flying operations. What are the flying operations? First of all, if you see the first slide, we have drawn some flight strips and aircraft is making the turn. So while making the turn, aircraft turns like this and it banks and again it turns back like this in order to reach to the next flight line. So we have some banking angle, and banking angle is limited to 25 degrees to 30 degrees. And what is the reason? The reason is, first of all, the flying crew should be comfortable, and they are generally comfortable around this value, right? Because this value will ensure that I will take minimum time to fly. At the same time, this turn should be comfortable also. If I increase the turn to 45 degrees, it is possible to make the turns, but flying crew will not be comfortable. At the same time, I will have a danger of losing the GPS lock. So we should be very, very careful on that part. So that is the role of banking angle here. Then we have cushion period. What's the cushion period? Okay, when aircraft turns from one flight line to next flight line, it will have some kind of cushion before it starts the data acquisition, that is the starting of the next flight line. And this period we should have to provide to the pilot, and that period is around 30 seconds to 60 seconds. And it depends on the pilot, person to person. In case of helicopter, since helicopter can do the sharp turning, this period reduces to 15 to 30 seconds. And in case of aircraft, it is 30 to 60 seconds. So it depends on pilot which value he prefers. So we have to provide some provision for this kind of cushion also. And that cushion period is very, very important, because during this period only, a pilot ensures that aircraft is smoothly flying, or it is going to fly smoothly over the next flight strip after turning. So after turning, he takes this much of time, right? So then speed of the aircraft should be constant. Okay. Now what about the maneuvering? Okay, maneuvering can be done on the consecutive lines, or it can be done with the larger turns. And so it will be not on the consecutive flight line, but it will be non-consecutive flight lines. So we have some kind of non-consecutive turning and we have consecutive turnings. Well, we are not talking all these things in detail, but I am just giving you some hints here. Then we have minimum height. the Director General of Civil Aviation specifies the minimum height, and that minimum height in India is 300 meter as per the DGCA governance. So a pilot has to maintain that minimum height. That means for higher data density, if you see, if I have lower height or lower flying height, I can acquire very high data density or high quality of data, but we can still not come below 300 meters. So these things has to be taken care when we perform the airborne data operation. Then flight endurance. What's the meaning of flight endurance? We have certain capacity of flying in an air, and in general, whatever aircraft we use, they have some capacity around 4 to 6 hours, because according to the fuel capacity of that aircraft. So after 6 hours or within 6 hours, aircraft has to take off, it has to acquire the data, and again it comes back to the airstrip. So this flight endurance we should always consider when we perform the data acquisition in air. Now coming to the wind, okay, let us assume that wind is flying and aircraft is heading towards the wind, that is called headwind, and as a result the speed of the aircraft is lower and we get less data density. You can see the expression of the data density. The data density equals to F by BSBV. So if I have headwind, what will happen? Wind will be reducing, the effective speed of the aircraft will be V minus some delta wind, and as a result the data density will increase because wind speed is reduced. You can see when there is a headwind, what will happen? The data density will increase. So you can see the formula here. If my V is there and V is the aircraft speed minus wind speed, I will have less effective speed of the aircraft and I will get higher quality of the data or higher data density. At the same time, let us assume that there is a tailwind. What will happen? The effective speed of the aircraft will increase, and as a result we can see here that in case of tailwind we have data density equals to F upon Bs upon V plus delta W here, right? So delta W is nothing but wind speed here, right? So I will have inferior quality of my data, or data density will be less. So we should consider all these factors when we perform the airborne data acquisition. Okay, now I consider all these factors like sensors, we have project requirements, we have field limitations that I already explained you. Then we have some user defined preferences like cushion period of pilot or maximum banking angle for the flying crew. Then we have mapping requirements like what is the overlap and what is the data density or nominal pulse spacing. And then, so all these things are contributing to the cost of the data acquisition. So when we integrate all these factors together and we plan the data acquisition exercise by simulation exercise, and this simulation exercise is called flight planning. And flight planning is very, very essential before the data acquisition is really performed in the field. Why? Because flight planning only ensures that certain quality of the data will be acquired with certain mapping conditions, with so-and-so sensors, with so-and-so aircraft, with so-and-so characteristics of all the elements involved in the data acquisition. So that is very, very important aspect of the airborne LiDAR data acquisition. Now let us see that how to find out the validation or how to validate whether we get the appropriate data or not. So once, let us say you have acquired the data after flight planning, you went to the field and you acquired the data. Now how to ensure that your data distribution is uniform or not? The simple checks are there, and we are going to learn all these checks here in this lecture. First of all, we define a quantity called NPS. What is NPS? Nominal pulse spacing. And that is nothing but 1 upon root of data density. and I will tell you what's the reason here. See, the data density is given by in points per meter square, right? That is number of points in unit square area. Now I want to find out what is each point is representing, or how much area is represented by the each point of laser data. So I can say that if I inverse the data density, I will get the area per point, right? Now I can say if I take the root, I will get the size of the area, that is meter per point. That means I'll get some area like this, and I call this as dimension NPS. NPS. So I can say that each this box is having one lidar point inside that, right? So again, it is an average criteria because it is calculated from the another average criteria, data density, right? So we should understand that how to now validate this data density or the NPS. So what we'll do, let us say there is one swath here, and then this is my NPS, okay? So now this is the cell of NPS, right? So we have calculated what is my NPS. So now I will take the 90% of the swath. This is the 90% of the swath, right? Now I will divide this 90% into the boxes of NPS size. So how many boxes are there? I can see here, right? 1, 2, 3, 4, 5. Okay. So let us put these boxes in the center 90% swath. Now we'll check that each and every box should have the one lidar data point into this box. But again, we know that since this is a random sampling of data, what will happen? We say that first of all we'll take the 90% of the swath or the center of the swath, then we'll take that, we'll fit boxes of 2 times NPS. So boxes of size 2 times NPS. So these boxes are basically, this is my 2 times NPS. This length is also 2 times NPS, right? So now such boxes are there. Okay, so 90% of such boxes, each of the 90% of the such boxes should have the laser data. And then we say that if it is so, we have the data distribution as uniformly distributed data. So we have the uniformly distributed lidar data. So that is the check we always perform, right? Okay. Now what about the data density validation? Okay. So let us say there is a area, or what we call is AOI, right? So you might be thinking we have already verified the NPS, or indirectly we have verified the data density. But there is some debate here, and debate is the data density is again an average criteria, right? It is used for uniform distribution validation. However, it cannot be used for the data density validation. And so we have devised a new method now. What is this method? We will take, let us say these are the lidar data points, and now we will divide these data points into the triangles. And what we call here is triangular irregular network, or TIN. So now I know that each and every TIN here, or each and every triangle, is representing one lidar data set, or one lidar data point is representing one triangle. But we have different areas of each triangle. What is the consequence here? We have to find some way in order to report the data density. So what do? Okay, I will tell you simply. We take the 95th percentile of the triangular areas, right? So let us see in the next slide. Let us see, you have complete area, you have total 1000 triangles, say for example. Okay, now you have A1 to A2 and let's say A999 and a 1000. So these are the areas of triangles. Right? What will you do? First of all, you will take the order data. That means you are ordered the data. I am writing, let's say A1, A2 bar, A3 bar. You have ordered this data. So ultimately we have some ordered areas. So higher to lower or lower to higher, whatever. Right? Now you will find out 1 upon A1 bar, 1 upon A2 bar, and so on. Okay? So each and every term is now representing the data density, right? Because it is some point divided by 1 upon meter square, right? Each in this quantity. Okay, since they are ordered one, what will you do? You will take the descending order and then you will take the 95th percentile. So what will you do? What will you do? Let us say this is the descending order, or we can say ascending order here. Ascendingly ordered, so it will become automatically descendingly ordered. Inverse of areas of triangle. Fine. Now what we'll do, we will take here a data which will be 1 upon A bar 950 here, because we want to take my 95th percentile. And so they are in the descending order. What will happen? This quantity will indicate the data density, or I can say it is the point data density of the airborne LIDAR data. And this is the way we finally calculate the data density, right? The other way around is that if I take the F divided by BV, that is an average data, average criteria. But this way I have a point criteria or the point data density. So that is a better one. The point criteria is much better than the average criteria over a large area, right? So now we have validated my uniformity of the data as well as data density after the data acquisition. Okay, now after that I would like to tell you that it is very difficult. You might have understood by this time that it is very, very difficult to acquire the LIDAR data. Why? Because the LIDAR data is very, very expensive, because it involves many expensive resources. First of all, the aircraft, then we have the scanner, then we have GPS, IMU, and the whole logistics of the airborne data acquisition is very, very complicated, as we have seen in the whole lecture. And as a result, we can see it is not a night game ball or very simple game ball to find the or acquire the LIDAR data, right? It requires a lot of resources, a lot of cost, although the cost will be minimized after we acquire the data for very large area and we use the data for many, many applications. However, in order to understand, if we have some facilities that can provide me synthetic LIDAR data, that will be good enough for me. So here there is a one synthetic LIDAR data generation application, what we call is Limulator, and that is developed by IIT Kanpur, especially by Professor Bharat Lohani, and this is a free software utility. And this is the link. You can download this data, this software utility in free. You can download this software utility from this link and you can use it. And you can see that how can you generate the artificial LIDAR data for no cost. And now you can generate different trees, different buildings in this software utility, and you fix the parameters of the flight. That means you can fix the speed of the aircraft, you can fix the scanner characteristics like repetition rate, the PRF, you can fix the scanning frequency, you can fix any number of parameters that you want of the scanner, IMU, GPS, everything. And then you can see that what kind of data you get, the synthetic data, and then you can understand that how that laser data you can play with. So that is the best utility is available today, and that is free also. So use the Limulator, try to make some hands-on experience on that. It's very easy, right? So with this thing, we understand that how to acquire the airborne LiDAR data. Next, I would like to tell you, what about the terrestrial laser data acquisition? It's very easy. It is not that complicated. So we have some laser scanner like this, which is looking like this on the front face and back face, right? So now I want to acquire the laser data using terrestrial laser scanner. And let us say I have put my laser scanner in order to acquire the data of a railway bridge, right? So you can assume that train is not passing and you are acquiring the data. So what do? You specify the field of view, right? So that is my 3D field of view, and then you acquire the data like that. So this data acquisition animation is shown here. So you firing sequentially fired pulses, and by this pulses you are acquiring the data of the bridge site. So this is the way the terrestrial laser scanner works. Similarly, now we have the mobile laser scanner. In case of mobile laser scanner, the same laser scanner is mounted on the vehicle like Jeep or car or maybe a road four-wheeler. In that four-wheeler, we have GPS as well as IMU, and as a result, when it moves on the road, it will acquire the data of the buildings, and it is also registering the data at every second or even the fraction of the second. So that is the idea about the mobile laser scanner. So now we have learned that how to acquire the LiDAR data using airborne platforms, using terrestrial platforms, and using mobile platforms. Okay, we also learned what is the quantity of the data, that is data density, and what is the quality of the data, that is the uniform distribution, right? And other parameters we have already learned like swath, overlap, and all these quantities. So in this lecture, we have learned completely what are the attributes of LiDAR data and how to ensure those. In the next lecture, we will learn about the georeferencing or the geolocation process of the acquired data. And we will also learn what are the errors that is available in the LiDAR data. Okay, thank you very much.